In the last three examples, we had functions that were straight, and so, even though we had to use a trapezoid formula or a triangle formula or a rectangle formula to find the areas, it was pretty straightforward. Now, what happens if your curve is not straight? So, like, for example, what happens if your curve is bent, kind of like this one in this picture? Well, we have a process that we call the process of doing Riemann sums to find the area underneath the curve. And the process works like this. First, break up the area into multiple little rectangles. In this case, I'm using 8 rectangles. And if you want the area under the curve, what you want to do is build the rectangles and estimate the length and width of each rectangle one at a time. Get all the areas of all the 8 rectangles, add them all back up, and you get an approximate idea how much area there is underneath the curve. So we're calling this an approximation because we don't really get an exact answer by doing this method, at least not with a few rectangles, like 8 of them basically. But I'm going to explain how this method works, and we're going to use it to do a few problems, and eventually we're going to say this method takes too long. It's kind of not exact because it gives an approximation always. So let's find a better method, and that method is going to be called Fundamental Theorem of Calculus. But for now, here's what the process looks like. So I'm going to be doing a problem here where the function f of x is equal to x squared plus 3. So the function that you have drawn right here is the function called x squared plus 3. It's kind of bent. It's not a straight line. So I cannot use the triangle formula. I cannot use the, trapezoid formula or anything else. And I would like to know the area from 0 to 3. So, when x is 3, this is where the y is. So my job is to find how much area there is inside of this region right here. It's not a trapezoid, like I said. It's some weird looking shape. 3 sides are straight, but the 4th side is kind of bent. So how am I going to find this area in yellow? The idea is make the 3 rectangles and figure out the area of the first rectangle, the area of the second rectangle, the area of the third rectangle, and add up those areas together, and you get an idea how much area there is underneath the curve in yellow. Obviously, we're not catching all of this, we're not catching all of that, and we're not catching all of this right here when we do this method, but still, we get an idea what the area looks like. So the area underneath the curve is going to be the area of rectangle 1, and area of rectangle 1 is going to be that rectangle, and plus area of rectangle 2, which is that rectangle, plus area of rectangle 3, which is that rectangle. And don't forget, the areas of rectangles are length times width. So the first answer right here is going to have 2 numbers that will be multiplied. The second rectangle is going to have 2 numbers that will be multiplied, the length and the width. And finally, the third rectangle is going to have 2 numbers, the length and the width, and they will also be multiplied. So let's take a look at the graph and figure out what the length and width of each rectangles are. So for this problem, I'm going to use pink for the width, and the width is going to represent this amount from here to there. So how much space is there from this point, which is the origin, 0, to this point right here? How much space is there? Well, it's just one step. So it's just 1 unit from there to there. Okay, what about if I look at the space from 1 to 2, how much space is there from 1 to 2? So it's kind of obvious. 2 minus 1 is going to be 1. So the second rectangle has width 1. What about the third rectangle? To go from 2 to 3, how much space is there between 2 and 3? Well, 3 minus 2 is going to be 1. So again, the height or the width or whatever is 1. So for the first rectangle, the amount is 1. The second rectangle, the amount is 1. The third rectangle, the amount is also 1. Perfect. Now, what about the height of the rectangle? How high is each rectangle? So like right there, how much is that amount on this graph? Well, the amount is going to be the y-coordinate of the point on the graph. So whatever the y-coordinate there is, that's how big the rectangle is. And remember, how do we get the y-coordinates? By using the function. The function is x squared plus 3. So what's the function at 0 doing? How high is the function when you plug in 0? 0 plus 3 is going to be 3 at the end. So the function is 3, and that goes right there. So that's how high the first rectangle is. When the x-coordinate is 0, the y-coordinate is 3. Okay, what about the second rectangle? That's this right here. So how big is that side right there? Well, again, the way to get it is to plug in the number on the x-axis into the function and just add a 3 at the end. So the number on the x-axis is 1. So when I plug in 1 into the function, I get 1 plus 3, which is 4. And that number goes there. Then finally, the third point, its x-coordinate is 2. So what's the y gonna be there? That will give me the height of that rectangle. So what's the height of the rectangle when you plug in 2? So again, let's investigate by putting 2 into the function. F of 2 is gonna be 2 squared plus 3. 2 squared is 4. 4 plus 3 is gonna be 7. So that number goes right there. And that tells me that the height of the third rectangle is 7. Okay, so the 3, the 4, the 7 are the heights of all of the rectangles. So now I am basically finished. 1 times 3 is 3, 1 times 4 is 4, 1 times 7 is 7. So together that's going to be 17 units squared. So the area underneath the curve is approximately 17. It is not exactly 17, it's approximately 17. I know it's approximation because, like I said earlier, I am missing a lot of space, right? All the stuff right here I'm missing from my calculation. All the stuff I'm missing from my calculation. All the stuff is missing from my calculation. So how can I improve my calculation? Make more rectangles, or make them thinner, or use a different method. Riemann sum that's not using the left endpoints. Maybe that uses the right endpoints or something else. Why do we call it left Riemann sum, by the way? We call it left Riemann sum because for every rectangle, I use the point on the left to find the height of the rectangle, not the point on the right. That's why I'm calling it the left Riemann sum. So sometimes instead of writing the word area right here, sometimes in your book, they will use these symbols, L3. L for left Riemann sum and 3 because I used 3 rectangles. In part 2, we're basically looking for the same area, except this time we are using more rectangles. So this time I have how many rectangles? I have 1, 2, 3, 4, 5, and 6 rectangles. So the accuracy should be improved when you use more rectangles. So let's start it off first by writing L6. This is because I'm doing left Riemann sums. I'm using the left side of every rectangle to figure out how high the rectangle is. And what I'm going to be doing is adding the area of rectangle 1 plus area of rectangle 2 all the way to area of rectangle 6. And keep in mind that each rectangle has a length and a width, so each rectangle is going to be 2 numbers multiplied by one another. Okay, so now that we have set up the formula, let's go ahead and look for the numbers. So first of all, what are the numbers on the x-axis? So the first starting point is 0. This point right here is 1. This point right here is 2. This point right here is 3. So the middle would be 0.5, the middle would be 1.5, and the final one would be 2.5. So those are the middles of all of the original intervals. So for the first point, remember the f of x in this problem is the same one from the previous part of the problem. It's the same f of x, which is x squared plus 3. So we're going to use it to find all these heights of the rectangles. So like for example, for this one, what's the height of the rectangle there going to be like? You just need to do f of 0. So 0 squared plus 3, which is going to be at the end, just simply 3. For the next one, the height of the rectangle is going to be the f of the point right there. So that point is going to be 0.5. So we need to put 0.5 into the calculator, square it, and add a 3 to it to see what the amount should be at the end. So the amount turns out to be 3.25. And we do the same thing again for the next one, and the next one, and the next one, and the next one. So go ahead and square the number that you have on the x-axis, and then add a 3 to it. Whatever number you get, put it right there, and do it 4 times in a row. So I'm getting 3.25, and 4, 5.25, 7, and 9.25. Now, how wide is each rectangle? The space from 0 to 0.5 is half a step. It's 1/2 a step, so 1/2. Same on the second rectangle, same on the third rectangle, same on the fourth rectangle, and so on and so forth. This is why in the future when I do these problems, I'm going to just factor the 1/2 out and just write all the other numbers inside of a parenthesis. Since the 1/2 repeats multiple times, I'm just going to factor it and write it on the outside to save myself from writing it 6 or 7 or 8 times. Now, the second number is going to be the height of each rectangle, which is 3 for the first one, 3.25 for the second one, and 4, then 5.25, 7, and finally 9.25. So again, when I factor the 1/2 out, it's going to be 3 plus 3.25 plus 4 plus 5.25 plus 7 plus 9.25. So that will make it a whole lot faster to find the area. And so now all this just goes into the calculator and we end up with some random number. So 18.875. And notice that the original number that we found on the first page was roughly 17. This time it's 15.875. So this seems to be a little bit of a better approximation.